How's it going, everyone? Welcome. Eliar Gonzalez here, looking right now at the asynchronicity in JavaScript and understand how do we get here. So, if you have followed me along with all of these courses and videos that where I'm taking notes out of this, the point of this is because as a UI specialist, we want us to now build and design front-end scalable web applications, right? So there are several cores out there that actually now I'm taking notes out of this and make some videos about it as a way to now create all of this story to make sense of how do we get here, which start by understanding is the fundamentals of the front end, by looking is at now how the browser treat HTML elements and that kind of things. How you can now is use is the GPU instead of CPU, which all the browsers actually use CPU intensively, but now modern browsers actually allow you to take advantage of the GPU. So for example, when you're using now is CSS property like transform, you are now telling to the browser, hey, we would like us to use now is the graphic layer. And there are some other CSS classes you can use as a way to skip this reflow phase. The reflow phase is just part of the way of how now the HTML, CSS, and JavaScript is parsed into pixel on the screen into pixel on the screen by the browser. So because this has a particularly different phases, all right, so you have now is the HTML, CSS, and JavaScript that is transforming to a DOM in CSS object model, which contains all the information about the structure and how it's going to look like, that is merged into now the render tree, which contains all the information that the browser needs as a way to, well, put these elements into that. So what is the structure, how these elements are going to look like, and how does it fit? However, it doesn't tell them how this element is going to put on the screen and what is the geometry of this. That's the reflow job. And after that, which is something that can be easily triggered by JavaScript by modifying these CSS classes, then you pass for this layout phase inside of the reflow that is actually now calculating is the position and the geometry of all of these elements on the screen. And then you have now the paint, which is actually how the browser now transform your digital image, this information, okay, into digital image, into raster image, this bidimensional array of pixels, where each one of them represents is the intensity or the amplitude, the change over time of RGB, red, blue, green, and the CMYK, right? So this is also interesting because now this step of how now the browser is going to paint all of this elements on the screen. So because you can create now stacking context, which means is that slice of these elements or this user interface as a way to now, when it comes to compose them to show something to the user, this is now the last phase of the entire process. So, and after that, this is when now the browser parses the JavaScript files, and this is a process that is synchronous. This is a process that is single threads. And here's when the interesting part kicks in, because since we're now building this user interface and the reason of building this in a much more maintainable way. So some companies like Meta, formerly Facebook, now they realize that in a way to actually make this much more maintainable and easy to work with, we need to have some sort of framework that allows to do much more easy to work with, especially when you want to render it from servers like PHP or Python, right? So they come up with this particular framework, this particular way of how you can now is describe user interface instead of an imperative way, in a much more declarative way. You just tell by using this functionality that they know what to do. You just only, allegedly, what at least in theory, focus is on building this user interface. However, this comes with some challenge in itself, and that is by building all of this user interface pretty much like this, right? By building all of these buttons, and each one of them has a particular data or state that it needs to manage, all right? The question is that how can we now control about which user interaction is being dispatched, okay? And now at least have a record of what are the interactions that happen and what is the next interaction, right? So as a way to actually is have a control, have a some sort of control mechanism when we need to actually is apply this, right? So because of this, we need to know is now an state for that, okay? As a way to now is make sense of how this actually started to, how can we manage all of this different change by the user interface, and we're talking about only from the human inputs, because there are other inputs like computer inputs where you have now for example is rendering image, okay, waiting for an image to get rendered, or waiting for a server to get some data. Now on that, okay, that's where this particular state management concept kicks in, and this is for React application. And bear with me because we're going to get here to the JavaScript and the asynchronous path, right? So because now the problems that when you're writing is this user interface is for the state, okay, which is, hey, how you can now is maintain the different states of all of this user interface, all right, as a way to now provide the features to the user, and also have a way to control, to have a certainty of when that happened, and all of this change mutation or state mutation. That's why there is a particular architecture called Flux that now, well, set up the foundation of this Redux application, this way of how we can make the state management maintainable. And then, well, some of the design philosophy as well as the intent and the goal, and how now that evolved in a way to say, hey, because now we know at least how can we actually is make our state mutations maintainable and predictable. So by using is now the Flux architecture, and this Flux architecture is made of actions, reducer, and then the actions, and then emits events to all of those components that actually are listened to, all right? That's why we need is to slowly but progressive introduce all of these functional programming concepts. So for example, like purity or immutability or partial applications and curing, all right, which might sound very weird words, but each one of them has now a particular meaning. The case of the purity is that given the same inputs, you're going to get the same output. And also immutability means is that it's going to create now a control layer around this data, so we can now have is much more better predictability when we update the state. In the case of the partial application and querying are useful because anytime you want now a specialized function, all right, you can use partial application when you preset some of the arguments, and on next call you provide the next argument, and the querying is pretty much this part, like the partial application, but instead of passing is multiple arguments, you're gonna pass is one input, and you're gonna get one output, one input, one output, one input, one output. So the idea of this is that it makes much more meaningful and easy to track when you apply now some change, or when you want a function to be more specific, right? As a way to provide now more specific features that in Redux, okay, especially because now when you need to handle this application that communicate to a server, okay, or that they need to wait for something, all right, that's when now we're starting to look at this middleware concept, which is the way of how now you can is intersect the actions and reducers. But in other words, this is a way of how you can now intersect when a mutation is going to happen, and then now perform some side effects. So for example, you want this to actually, in this case, like, hey, you want now to actually look at your calendar, okay, but your calendar live in another server, right, in another application. So that's why you have to wait for this to be loaded and then show them properly, or your Google Keeps, right? So next subsequent call actually loads and that is already there. So this particularly asynchronicity, okay, that is what we're going to take a look at now, is important as a way to understand is this conceptual asynchronous pattern, and then a more hands approach, as a way to make sense of why we need to look at this asynchronous pattern, and to understand the sort of difference between parallel and asynchronicity. Because first we got now is this concept of parallelism, which is unlike humans. We as humans, we are not truly parallelism, even though that we think that we can do multitasking, all right, or even though that we might think that we are multitasking. So hey, you answer the phone, and then while you're sending an email, or you're drinking coffee while you're reading the news, you know. But cognitively speaking, I am not a neuroscientist, but cognitively speaking, we are not as truly parallel, right? So for the biological perspective, there are certain things that need to happen as a way to keep us together. And we don't actually blow it up, you know, or we just melt down. So in the context, in the computer context, parallelism means that, or parallelism is expressed in threads. So one threads on my CPU, so one threads here is this kind of queues of operations of this small unit of execution, okay, that they're going to happen at the same time. So for example, if you're looking in a common CPUs where you have now 8 or 12, 16, 32 threads, you can think that, and especially if you now run an OS, that's something that is not, you need more than that. So for example, just only running a browser, it actually runs on it actually run is what it actually needs 4 threads. So if you open up now in 2024 the Chrome, for example, and then you open up the task manager, you see that now actually just for just being there, for just be alive from a fresh start, from scratch, it needs 4 threads. All right. So this particular process, you can imagine that an OS needs, of course, tons of process to actually provide you the thing that you need to work with. So this process and threads, the subtle difference is that this process is this program, it's an independent program that has its own resources, own memory. However, threads are this small unit of execution. What does it mean? The small unit of executions in a process. What does it mean? That in the context of JavaScript is that because now this language is single threads, the small unit of execution is one line at a time, right? So for the cognitive perspective, this is something great because it resembles a lot of how do we plan and write code, okay? So we don't have to actually worry about this parallelism and how different process can communicate, and how different now executions, small unit of executions communicate each other. So because now JavaScript is single threads, there's some ways of how you can try to make this multi-thread. So for example, like using web workers, where you have now this particular process that is running and now have the ability to share its states across all of these different JavaScript engines that is running on different process, okay? But again, this is not a feature from JavaScript. This is a browser feature, okay? It's a browser features. So here you don't have to deal, for example, with things like semaphores, semaphores and new taxes and resource locking or share resource locking and all that wildness things. So that's a great thing for us as a JavaScript developers. However, with the way of how we going to handle this task that overlaps over time, so now web workers give us this communication through a step or asynchronous event, okay? So we have now this notion of the event loop. So because concurrency is a thing that we have to manage when it comes to provide solutions, in this case with JavaScript, right? So instead of looking at this like parallelism, which in our case, since we're writing is JavaScript programs, which means single thread applications, we need to define is this particular problem, concurrency. And concurrency is the ability of a system, and there's several concepts out there. I'm just mentioning is the one that come from Kyle Simpson. Shout out to Kyle Simpson. Deeply respect, man. Despite that you don't have right now is a job, but it doesn't matter. You'll find one. Trust me. Okay. What the French does? Okay. So this concurrency, which is now the ability of a system to deal with multiple tasks that overlaps over time, okay? So is this complexity, or is the complexity of dealing with multiple tasks that overlap over time is what we need to take care of us, all right? So every async pattern we're about to see can be achieved with callbacks. Some of these async pattern is like thunks, promise, and then we're gonna see callback, thunks, promise, then generators, then event reactive observables. But that's where now the value proposition of all of these things come into place. Oh my god, sorry. So we're going to see exact in because at the end of the day, because we need to deal with this kind of concurrency, which is one of the complexity, especially when we need to write these own applications here. For example, e-commerce applications, where they need to actually is at the checkout button deal with this thing that is triggered not too much, not too fast, so not too many, not too early, not too late, not too fast. Keep up the context. Don't split errors, or don't swallow errors, and all that kind of stuff. So this particular complexity here that we need to handle, callback is an insufficient way to express that. Based on the complexity of all of these things that we need to handle, all of this use case for that. That's one of the reasons why the next level of competency as a JavaScript developers is to be strategic and tactical in your approach of concurrent management for a single applications. Again, this is if you're going to really dedicate to JavaScript, which is in my case, yes, JavaScript and TypeScript, right? So, okay, that's interesting. So then we started to look at callbacks. Again, the goal of today's video, all right, is to now look at thunks, briefly describe how do we get here with thunks, and then now jump into the promise. Okay, so because the way of how can we deal with these asynchronous operations, okay, is using callbacks, okay, like this. So hey, callbacks after all is the continuation of a program at some points in the future, right? So by passing is an X amount of, so by running this particular code at an X amount of time here, we hope that this program, or that this at some point we will be able to run that continuation. We will be able to run that program, right? So some people actually complain that one of the problems of this callback is that this thing known as the callback hell. Okay, so where here in the callback hell you say, well, you actually now have to pull all of this nested stuff that actually is hard to read and that kind of thing, but you can actually reorganize in this particular way, right? And even though it doesn't solve the problem of how our brain works, what we need to handle is this asynchronicity. So because even though that it can be now not only hard to read, which is one of the problems with this, we also look at a particular example of how using callbacks for building user interface. So for example, you have to make multiple requests. It's like, hey, I want you to fetch these CSS files, as well as its fonts, as well as the analytics scripts, as well as the HTML elements from the home page, right? So because you want to now fetch all of these elements in parallel, okay, you need to also is waiting for them to come back, process them, or coordinate its response, respond accordingly, respond as soon as possible, and find a way to now is provide an order of that. In other words, that make sure that all of these things happen in order. Make sure that all of this request callbacks, or all of this requests, which is the issue is not on the request, the issue is that is on the response of how do we get this data. Okay, how by waiting for this data to come and then coordinated response and coordinated response in response as soon as they are available, and show them in a particular order. All right, a lot of this time is something that requires some solutions, tricky solutions. All right, so for example, in this case, where we have now, we're going to have now a global record of response, where here we're going to actually every time we make this particular request, we're going to handle is now this incoming request. Okay, so if they exist in your record, good. Now let me see if they are in the proper order that we get it. So that's what we are using here, an array, right? And we are actually hard coding this, which is data from this, just for the sake of the example, as a way to see how we need to coordinate this, and then how we're going to respond as soon as possible. Respond as soon as possible, and show this response in a particular order. Again, this is a solution that works. All right, and this particular pattern now actually works. All right, so you have one record, and in this record you're going to actually manage all of these things. The problem is that this is like plumbing. Okay, so the problem with this is anytime you need to actually do this or handle this asynchronicity, all right, a lot of the time you will need to not only write this particular logic, but it doesn't make sense of this, and it's not. This is one of the problems of the callbacks here. Where we talk about is this inversion control with the callbacks. What happened is that let's use a more simple example here. What happened with this callback? Exactly. What happened with this callback is, hey, I'm going to now have I got a first half of my program. Okay, so the first half of my program actually now is the first half of my program, which is something that I'm in control, and the second half of my program that is not in control. The way of how can I express this asynchronicity, or this waiting for this data or waiting for this continuation of this program, okay, is that I'm going to run the first half of my I'm gonna run to the first half of my code, and then use a callback to pass the second half, which is where I invert control. So I put them in control. In this case, the web platform, the browser or the server. Okay, I put them in control of when and how that program will run, or that command will run. So this is one of the problems here with this inversion of control. And this not only generates trust issues, because especially if you have now an e-commerce where for some reasons when you click on that checkout button, this e-commerce is now selling is smart TVs, and this smart TVs is something that your boss actually hired you to actually build, not only the user interface but also to manage is the payments as well. So you did it, all right, which is a great thing. Now You check that everything works as expected. In this particular function that we got here, you actually put your trust in this function. It actually works as expected, which is a great thing. You test that, and then you deploy it. Good. 6 months later, you are sitting in a coffee shop with some pals, and then you receive now a call from your boss, which is quite not casual self, you know. And he's quite desperate about that. Hey, we charge East Kanye West with several TVs, and he didn't purchase that. I need you to get your ass ASAP. You go back to the office. You try to understand what went wrong. Okay, and then now you do your heuristics. So you make sure that your code actually works as expected. You logically come with a conclusion that actually works as it is. Unlike this particular function here that is outside of your control, is something that you are now using as a third-party library, right? So you reach to this point, and then, you logically conclude that the problem might be there. Okay, so you check of how they're doing this kind of thing, especially with the timers, and they are now actually firing these things as within a particular X amount of time to check if that was used. You try to read the documentation, and there is nothing about that. So you contact their customer support, and they tell them that is quite interesting, that it doesn't appear on their docs. So they raise that ticket to the developer. But while you are now waiting for that, you need to have some sort of fix, right? So hot fix. So you say, hey, let me now put now this flag, right? So you feel proud about yourself. So because by the time it reaches to this, by the time you call this function, okay, it is now something that you're going to check, right? If that has been so you can now charge the credit card and show the thank you as it is, right? So good. So now you develop this particular code. You now pass that to the QA. So QA actually, we love QA, man. We love QA. Even despite that is sometimes a hate-love relationship, but we love them. We love them. And then now here, QA is starting to ask some questions. It's like, what will happen if this has been called is always false? All right. Or what will happen here, which is quite interesting. It's quite interesting. Very, very interesting.
So he says, well, what about if they never call our callback? Question that you didn't even occur to you. You didn't want them to ask, because
yeah. Then they ask you questions that you didn't even think about it. All right.
He says, well, what about if they never call our callback? Do we have any code in there for that? That question that you didn't even occur to you. You didn't want. You say, oh, I got this fix for the bug. Here's the reproduce case. Blah blah blah. And then that QA person does what they always annoyingly do. They ask you that question that you didn't even occur to you. You didn't want them to ask, because he says, well, what about if they never call our callback?
Mm-hmm. So what happens if they never call a callback? Here, you know. Oh my God. What happens if they never call this continuation of the program? What will happen there?
Do we have any code in there for that? Nope.
Nope.
So now you're starting to panic, like, no, I don't have a solution for that problem, but I guess I could set up some kind of timeout for that or whatever. And then he goes on, he says, well, what about all the other places in our code that we use callbacks? Do we have fixes for all?
And then it comes with all of these questions that, but what about the fixes for all of these problems? So do we have now some sort of fixes where our callback has no call?
All of this in all of those places? And you get that blank stare on your...
You know, is that what happens if this callback is never called? It's like, well, you just actually is now set a timeout for that, and then you wrote that code, right? And what are the parts of a program that actually never trigger that callback?
Your face, and you're like, maybe I can slowly back away and pretend I did not hear him say it. Maybe I just can pretend I didn't hear any of this, right? Because all of a sudden,
then maybe, no, I know, and maybe I can walk down a little bit and pretend that I never heard about this. You know, it's like, that's quite interesting. You slowly go back, right? But again,
what's been exposed is how deep this...
Exactly. and what QA has exposed is our deep now misunderstanding of how these things work and the repercussions.
This rabbit hole goes. The trust issues that were involved in passing a callback, the inversion of control trust issues.
That's one of the reasons. That's one of the things here that this callback here with this inversion of control now the QA team exposed by asking just simple questions about what is these callbacks never get called, right? And these things now are like, well, you want to make sure that this callback called not too early, not too late, not too many times, especially not too many times, not too few times, not lost context, no lost context, no shallow errors. Do what it's supposed to do, running that. And another thing is that these callbacks are not reasonable, reasonable, right? Because the way how now the JavaScript engine works is by this thread, is by having this line of execution. So, and the idea of this is to understand now how can we write is patterns that work of how our brains works. So you can imagine the JavaScript engine actually works pretty same like our brains, cognitively speaking, okay? In this task that overlaps over time. And the point of this is that since we are writing code that is look like synchronous, and we can make sure that all of these statements actually evaluating one after the other. In the context of callbacks, expressing this asynchronous nature is not only have this inversion control, because we are now passing, or we put them in control of when and how this portion of this code is going to be executed, all right? But also is in terms of readability, is not reason about it, right? Because again, as I mentioned before, with JavaScript being a single thread application, single thread language, evaluating statement one after the other. So what are the fixes or the non-fixes, as I mentioned here? Well, one of them is to say, hey, let's go to now put a particular function, all right, that now be able to take is this two callbacks. So one of these on error and the other is on success. The thing here is that what will happen is this function is never get called, right? Or the second function is never get called, all right? If the errors never get called, or the OK is never get called. So now we're starting to have this same trust issue here. And that's say, well, okay, let's go to now, instead of doing that, is this error style, you know, it's this error first style, which you're gonna pass now a callback here. And by the time that now this value or this time has passed, we're gonna now continue the programming. We're gonna now continue this execution of this statement here. And that's what you have now. As the first parameter, you're gonna receive the error, and the second, the num. And the other is that's great for doing one single thing, okay, for waiting for the data to be loaded. But what is when we need to actually do multiple things at the same time, or this is a fancy word to say, hey, time dependent data, right? So when you need to wait for one, you need to make a request, and then once you get that data, you then need to make another request, and so on and so forth. This cascade, right, or this nested callback task. Again, this is quite interesting to describe, because this is now doesn't work the way of how our brain works, okay, by looking at those things that are sequential, blocking. And here are some of these particular patterns of how can we now solve this. So for example, Thunks. In Thunks, we have now synchronous and asynchronous perspective, okay? So from the synchronous perspective, we have now this is a function that have everything that it needs to do and give you a value back. So this act like a token in our code. So anytime we call the function, we're gonna get is that value with these presets things, right? So the thing here with Thunks is that because JavaScript has a particular feature when you need to when you return is a function, behind the scene you say, hey, let me now save this reference of this function as well as the data around it. So this is part of the closure aspect of this. This pattern now not only unlock things like model patterns, immediately invoke function expressions, and things like promise, which is something that we're gonna see that, as well as iterators, all right? But because the whole point of this closure is that we have now the reference of the functionalities, this function reference, as well as all of the data around it. So Thunk, from this synchronous perspective, is this particular way of how you can now have a container that this function have everything that it needs to do, in this case at 10 to 15, all right? And we're gonna get that back anytime we create or anytime we call to this Thunk. It's gonna have this token of this. So far so good. When we talk about now in an asynchronous fashion, and that makes a lot of sense. Crap. So when we now look at this in an asynchronous fashion, is that yes, this is now a function that have everything that it needs to do, except that by the time you get the value out of this, or except that it's going to take a callback to get the value out of this by the time it receives that. So this is something, this is huge, because we are now be able to decouple this time from the equation, which time is one of the most complex factors to deal in our application, okay? And we can now run these callbacks to get the value out of this when we need it, right? And this is huge. So however, there's some twists, some wrinkles that can throw to the situation. So for example, if you want to create a generalized utility function, for example like this, and you want to create this make thunks, where you take all of these arguments here that you're receiving and now putting them into an array here. You're reserving space and memory for all of these arguments that you are receiving in this thunk, okay? And then by creating is now this function reference, with this callback, in any time we now, this is a way of how you can create a record here, right? Because that's pretty much what we're doing here with this slice. Array slice, right? Because what you're doing is just returning a shallow copy, right, of a portion of an array into a new array object selected from the start. So by doing is now slice here, you say, hey, slide.call slice slide.call, and call is from the function, okay? Instance call this function and give this value an argument provided by individual. Okay, call this. Okay, so what you're doing is that, hey, I'm creating is now a new array, okay, that I want to slide is now the argument that I'm gonna pass to these functions here, which is anytime you actually create this function here, is now going to parse that. Yeah, name it. Okay, it's gonna take all of these function arguments here, all right, and then by the time you now create the Thunk, this function's reference, where you're gonna pass is now a callback. By the time you call that, it say, okay, now let me actually is push all of this. The idea here is that with the call is now actually making the value of this to point into the arguments, that they have in this function, right? Which is this. So call, bind, and apply. That's where you have this. So the subtle difference between call, bind, and apply, right, is that apply and call actually is the way of how you can pass now not only the value of this, okay, as a way to now make this, as a way to actually is inject some of the properties to this function execution context. The call and apply, that's what you do. It's like, hey, I want you to pass now this value, all right? But now the way of how apply and call actually receive this argument, apply receive that in an array like, whereas call that is by comma separate values. And bind, okay, is a way of how you can actually is, whenever this function call, this is what you're going to run. So the bind method function instance create a new function that when call this function with this keyword. So this is something interesting here, because this bind function, okay, it say, hey, by the time you call this, function, this is now the value of this that I want to have inside of this function execution context, right? Exactly. So the whole point of this is that with bind you can now actually, as the name suggests, is pass the value of this when by the time that this function gets called. So this way of refreshing things, which is very, very important. So here you create now this array that is going to have now all of this is slice. So it's going to call that, where it say, hey, okay, I'm going to call this, So call here say is like, hey, I'm going to call now is those functions. Here I'm gonna call now those functions with this argument or with the value of this, okay, as a way to now store is the argument from this function, okay. And then you say, okay, so by the time, so this is what you're doing here is not, it's just having a record of this functioning in its arguments, right? So this is pretty much what you're doing here. You just have a record of all of these arguments here, and by the time that this function gets called, okay, you have now these arguments, functions. All right, you say, hey, now this callback, I'm going to push that as an argument to this. Interesting. Now I'm going to put this callback as an argument here. Okay. Okay, this callback will be a new argument here in this array, in this record. And then I'm going to now run that function that I receive here with this argument, with these arguments as well as the callback here. So apply what it's doing is that, hey, this is what I'm gonna do. It's now calling this as an array like. Interesting. Holy F. So by the time you call this, okay, so by the time you call this function or this thunk, okay, and then this thunk now is going to execute this particular callback at this amount of time, you can now effectively creating is this particular way of how you can now keep track of your or your argument. So you have now a function that allows you to is store the values or have everything that it needs, and then pass a callback to get the value out of that. Jesus fucking Christ. To get the value out of that. And that's what we started to look here in an exercise as a way to exercise, as a way to make much more sense of what we're doing here. Is this exercise? Let me take a look at this. Like so. Okay. The exercise here. So in this particular exercise, we look at when we need to create this particular thunk, which will be tokens, okay, to the eventual completion of something, and then we get the value out of this. All right. By the time we create these tokens here, so when these values are done here in this get file, which is now how we can create is this particularly thunk. So get file is a thunk. Get file is now this thunks that allow us to actually have everything that it needs. And then by the time you pass a callback in the context of async operations, you get a value back. Okay. So this is now when you implement this get files, and because there are two possible things that can happen in a thunk, which is either or. By the time you call this callback function, you already get the data out of it, or you don't have it, and then you have to wait for the data to come back so you can let it undo that. This is exactly what we're doing here. This is the two possible scenarios where this function needs to handle here. and that is both of them are time dependent. So, or by the time you call this callback, you already have the data that it needs to. Okay, which, well, now it is time to run that callback with that data, or you need to actually is somehow to store that callback, and then when that is ready, actually run that callback here. Holy French toast, guy. What the fuck? When I see this pattern, to me it's like, oh my god, but I don't know. I don't know what in the F I have done with my. This exposed that my lack of understanding of this particular tool and how to use it to come out with some sort of solution, and especially when we need to describe is the problem. So far this is something that we say, hey, this is great. This particular pattern doesn't require any third-party libraries. In fact, this actually will solve in any programming language, as long as they now have these closure features that allows them to hold is a reference in memory for that. Holy moly. So we're gonna see now is that what are the things that this Thunk, what are the problems that this Thunk, what is this particular async pattern solve, however, with still some pending tasks or pending problems that we need to solve here. Oh my god.
Judging, I know I can just go ahead and send it. Thunks are a thing that you can use. It's a very lightweight way of solving asynchronous.
Mm-hmm. And Thunk is a very lightweight. Oh my god. In solution. So Thunk is this lightweight thing that you can use to handle concurrency in your application. It makes a lot of sense here.
Sequencing issues without having to invoke some huge library or some crazy API or something like that. It's a very lightweight, easy way of doing it. It's going to take some practice to wrap your brain around that pattern. It took me quite a bit of practice. Would highly encourage you, between now and the next time we get together for this workshop, spend some time going back over that. Try that from blank file and see if you can recreate that same reasoning that I just recreated. It'll make our exploration of promises a lot more fruitful for you if you do.
Yeah, it'll make this exploration. Yeah. It'll make this exploration much more fruitful for that. Damn son. Oh, okay. This is pretty French toast, guy. This is pretty French toast, and it is all start by describing is how we're going to handle is this asynchronicity here in Thunks. Okay. Exactly. And not only that is how we're going to handle is this by the time we get this value here, and by the time we're not. So after all this Thunk or these closures allow us to define some sort of things that we need to. So closures allow us to define things that we need to store. Okay. And by the time that this function now runs, we can pass them to. So Thunk is now this particular concept where this is a function, it's a wrapper function that has everything that it needs to do to get a value back. This is from the POV. This is from the synchronous POV. From the asynchronous POV is that it's a wrapper function around. It's a wrapper function that has everything that it needs to, except that we're gonna pass a callback to get the value out of that. Holy moly.
That'd be useful to just very quickly circle back to kind of talk about this notion of what a thunk really is. And actually, it's not really all that special. It's just maybe a usage of the callback pattern that we aren't terribly familiar with. Most of us probably at least have some passing familiarity with closure. And that's really what the thunk is all about, is using closure to maintain state. Now, why?
Exactly. Using closures to maintain state. So, Thunk, what is using, so Thunk is using closures to maintain state. Holy moly.
Is that so important? I saw some questions on the chat before about, what are thunks? Are they solving callback hell or things like that? Well, they're still callbacks, so they're not fundamentally changing that particular game. Callbacks aren't really, thunks are not really adding anything to the equation in terms of better trustability, or even, they're a little bit more reasonable, I suppose. This code is clearly a bit more reasonable than what we had before with just regular callbacks. But it's not fundamentally more linear or sequential or synchronous in nature. So it really hasn't moved the ball much on that respect.
So Thunk is using closure to maintain a state. So they don't improve is okay. They don't okay, because it's coordination here. So Thunk is using closures to maintain state. They collaborate in the coordination of this. They don't improve callbacks. Because they don't improve callbacks. In fact, they use it. It's just that we have now a more readable code to handle asynchronicity. However, it doesn't remove the trust issues we got with callbacks. And not to mention that is not like, because this is a wrapper inside of the JavaScript. This is not native, that's what happened. And not to mention that it's not like how JavaScript engine works in this single thread fashion. One line after the another in the single thread fashion, in a sequence.
Correct. So thunks really aren't specifically about solving callback hell, but they do solve a really important problem that sets us up for the rest of the stuff that we're going to discuss in this workshop. And that's why I chose to spend time pushing on them. It's not just a trivia sort of thing. They really are an important conceptual foundation upon which we build the rest of stuff. So the major takeaway, why is a thunk so important to me? Why should I care? And why should it be something that's part of my arsenal of weapons that I use to take down asynchronous programming issues? Well, the reason for that is that by using the closure in the thunk pattern, by using the closure to maintain the state of something, we eliminate time as a complecting factor of state. Time is the most complex factor of state in your program. Understanding the order in which things happen and the way things change over time is the most complex part of your application. It's the hardest part for us to reason about. Is it impossible? Clearly not. But it does make it harder. So if we can use this tool, this notion of preserving state inside of this value wrapper container that we call a thunk, We then
value wrapper container that we call value wrapper container.
are able to compose these values together and not worry about the ordering. Time becomes a non-issue. As you can see here with this code, I am sequencing the Thunk 1, Thunk 2, and Thunk 3 together. And we know already, having looked at the previous solution, hopefully that's fresh enough in your minds, having looked at the solution, we see that there is basically a race condition, if you will, between whether we ask for the Thunk's response before it has it, or whether the response comes back before it's been asked. There's a fundamental race condition there. That's a time issue. That's a complexity issue that we had to manage ourselves in the previous exercise by writing all that for loop crap and stuffing things inside of a global variable. That complexity is something that we had to solve ourselves. This pattern solves that for us. It takes a value and eliminates the time as the concern. Doesn't mean it eliminates all concerns, but the most complex of our concerns is eliminated. It's not even really eliminated, it's just simply abstracted away, so it's not something we have to be concerned about in the parts of our code where we're consuming these values. So we write the plumbing once, if you will, the mechanism by which a thunk is created, as I showed you just there. And then where we use it, it's the lines 41 through 50 that represent the bulk of our code that we write. Over and over and over again, we write code to reason about asynchronous actions that are occurring. And this is the kind of code that is significantly more reasonable than it was before, because we don't have to worry about time in this issue. That's what is so important. And I'm harping on this so much because I think the next topic that we're about to talk about, we're about to jump into promises, and I think the point has largely been missed about why promises are so revolutionary. I think most people have focused on promises as an API.
As an API, exactly.
And to be honest with you, the API for promises is the least interesting part to me. It's far more interesting to me that promises are a codification of this pattern built in for us so that we don't even really have to think about it as much. It's even there for us automatically. A codification of this pattern of managing state internal inside of a wrapper in a time-independent way. There's more to promises.
In a time-independent way, because it's running is in a time-independent way, because in a time-independent way, because it essentially is this is a race condition. This race conditions. Race conditions. This is something interesting. Race condition is a race hazard. It's a condition of an electronics, software, or other systems where the system's substantive behavior is depending on the sequence or timing of other uncontrollable events, leading to unexpected or inconsistent results. It becomes a bug when one or more of the possible behavior is undesired. The term race condition was already used in 1954, for example, David A. Huffman. Doctoral thesis, the synthesis of sequential switching circuits. Oh my God. Race conditions can occur especially in logic circuit or multi-threaded or distributed software programs. God damn it, because it comes from the basis. Using mutual exclusion can prevent mutual exclusion can prevent race condition in distributed software systems. Mutual exclusion is a property of concurrency control which is instituted for the purpose of preventing race condition. It is a requirement that one thread of execution never enters in a critical section while a concurring thread of execution is already accessing the same critical section, which refers to an interval of time during which a thread of execution access and share resource of memory. In his seminal 1965 paper, Solution of a Problem in Concurrent Programming Control, which is credited as the first topic in the study of concurring algorithms. A single example of why mutual exclusion is important in practice can be visualized using single linked list of 4 items, where the second and third are to be removed. The removal of a node that sits between the 2 nodes is performed by changing the next pointer on the previous node. In other words, if node I is being removed, then the node pointer, exactly. When such a linked list is being shared between multiple threads of execution, two threads of execution may attempt to remove two different nodes simultaneously. One thread of execution changing the pointer will another thread of execution change the next pointer. Although both removal operations complete successful, the desired state of the linked list is not achieved. This problem, called race condition, can be avoided by using a requirement mutual exclusion to ensure the simultaneous update at the same part of the list cannot occur. Deadlock. Bound on a mutual exclusion problem. Okay. Race conditions. This happening is in logic circuit multi-threading of distributed software, where subsequent behavior is dependent on a sequence or timing of uncontrollable events. So if the behavior is dependent on a sequence or time or timing of uncontrollable event, exactly, or time, it leads to unexpected or inconsistent results. Holy moly.
And that, but that in and of itself is revolutionary. That in and of itself is bringing to the masses something which we could have been doing all along, but for whatever reason, this wasn't something that we spent time thinking about. I've written an awful lot of really bad asynchronous code. I wish I could go back and fix all of that stuff to have been using a pattern like Thunk's, because this would have been a lot better than what I had before. But it's not the end of the story. There's more to go, much more to go in this workshop. So you're not really adding anything to the equation in terms of better trustability, or even, I mean, they're a little bit more reasonable, I suppose. This code is clearly a bit more reasonable than what we had before with just regular callbacks. But it's not fundamentally more linear or sequential or synchronous in nature. So it really hasn't moved the ball much on that respect. So Thunks really aren't specifically about solving callback hell, but they do solve a really important problem that sets us up for the rest of the stuff that we're going to discuss.
Exactly. So this is now Thunks and closures. So Thunks and closures. Exactly, Thunks and closures. Thunks actually solve a very important problem in our code. These race conditions that can happen. Yeah, Thunks actually solve a very important problem in our code. These race conditions that can happen. Okay. Oh shit! These race conditions that can happen when dealing with sequence of data, when dealing with concurrent programming. So Thunks actually solve a very important problem in our code. This race conditions, which is time. These race conditions that can happen when dealing with concurrent programming by using closure to maintain the state of our by using closures to maintain the state of our async operation.
In this workshop. And that's why I chose to spend time pushing on them. It's not just a trivia sort of thing. They really are an important conceptual foundation upon which we build the rest of stuff. So the major takeaway, why is a thunk so important to me? Why should I care? And why should it be something that's part of my arsenal of weapons that I use to take down asynchronous programming issues? Well, the reason for that is that by using the closure in the thunk pattern, by using the closure to maintain the state of something, we eliminate time as a complecting factor of state.
So actually it solves a very important problem in our code, time. So by using closure, by using closures and store, by using
in the thunk pattern, by using the closure to maintain
the
state of something.
So by using closure to maintain, the state of something, we have eliminated this race condition of time.
We eliminate time as a complecting factor of state.
We eliminate time as a complexing factor in our state. These race conditions that can happen when dealing with concurrent programming. With concurrency. These race conditions that can happen when dealing with concurrency. Calling multiple servers to process, calling multiple servers to process a checkout in an e-commerce, for example. Calling a checkout in an e-commerce, for example. A checkout process in an e-commerce, for example. Exactly. A checkout process in an e-commerce, for example. So for example, a checkout process in an e-commerce. Exactly. A checkout process in an e-commerce. Processing transaction. Bank processing transactions. Okay. Bank processing transactions. Oh, crap.
Time is the most complex factor of state in your program. Understanding the order in which things happen and the way things change over time is the most
Understanding the order in which things happen.
Complex factor of state in your program. Understanding the order in which things happen and the way things change over time is the most complex part of your application. It's the hardest part for us to reason about. Is it impossible? Clearly not. But it does make it harder. So if we can use this tool, this notion of preserving state inside of this value wrapper container that we call a thunk, we then are able to compose these values together and not worry about the ordering. Time becomes a non-issue. As you can see here with this code, I am sequencing the thunk 1, thunk 2, and thunk 3 together. And we know already, having looked at the previous solution, Hopefully that's fresh enough in your minds. Having looked at the solution,
So
we see that
solve
there
this
is
race condition here.
basically a race condition, if you will, between whether we ask for the Thunk's response
When we
before
ask
it
for
has
the-
it, or whether
Exactly. When we ask for the Thunk response before, when we ask for the Thunk response before it happened, but when we ask, okay, when we ask the Thunk, when we ask the Thunk response before it happened,
the response comes back,
or the response come back first,
before it's been asked.
or the response come back, or the response come back before the callbacks
Asked. There's a condition, if you will, between whether we ask for the Thunk's response
when we ask for the Thunk response
before it has it,
or
or whether the response comes back
or whether the response come back
before it's been asked.
or whether the response is being asked. Okay.
There's a condition, if you will, between whether we ask for the Thunk's.
So yeah, this is race conditions here. So we are now abstracting this time. Exactly. So we are abstracting time from. So we are abstracting time here. So we are abstracting time. Exactly. So we're abstracting time by using a closure to keep. By using a closure to maintain the state. Damn. So we're using a closure. Okay. So with Thunks, we're using a closure to maintain the state. To maintain the state of this async operation of this. And we are limiting time as a complexing factors. Time as a complexing factor. So we're using now an state. So this is fucked up. So we're using now an state. So we're using closure as a way to keep some state by eliminating is the factor. By eliminating time as a complexing factor. Oh shit. God. So we're using now this concept closure, this tool, to store some state to eliminate time as a complexing factor by handling is this race condition. So by using closures to maintain the state of something, we eliminate time as a complexing factor in our state. Solving this race condition. So you are now mutually excluding that. Solving this race condition. Solving race condition. Solving race conditions that can happen with dealing with concurrency. And this is the true problem of this. This is the true problem of this. Is this race conditions? How can we handle this race conditions in concurrent programming or in concurrency? For example, a checkout process and an e-commerce. Oh, crap. So here we have now this. So here we are using is now this is state. God damn it. Here we're using now this is state to store something that eliminate time as a complexing factor that now solve this race conditions here. This race condition is that whether this response actually gets called first, whether is the response comes first than when we're calling our function. Okay. Or calling this or assigning, replying this data after the replying with the data after the response have come in, or before the data, or before the data kicks in, or setting everything that it needs to before the data kicks in.
Response before it has it, or whether the response comes back, basically a race condition, if you will, between whether we ask for the Thunk's response before it has it.
Before where we ask here the Thunk response before it hasn't, which means that, hey, you don't have that,
or whether the response comes back before it's been asked. There's a fundamental race condition there. That's a time issue. That's a complexity issue that we had to manage ourselves in the previous exercise by writing all that for loop crap and stuffing things inside of a global variable. That complexity is something that we had to solve ourselves. This pattern solves that for us. It takes a value and eliminates the time as the concern. Doesn't mean it eliminates all concerns, but the most complex of our concerns is eliminated. It's not even really eliminated, it's just simply abstracted away, so it's not something we have to be concerned about in the parts of our code where we're consuming these values. So we write the plumbing once, if you will, the mechanism by which a Thunk is created, as I showed you just there. And then where we use it, it's the lines 41 through 50 that represent the bulk of our code that we write. Over and over and over again, we write code to reason about asynchronous actions that are occurring. And this is the kind of code that is significantly more reasonable than it was before, because we don't have to worry about time in this issue. That's what is so important. And I'm harping on this so much because I think the next topic that we're about to talk about, we're about to jump into promises, and I think the point has largely been missed about why promises are so revolutionary. I think most people have focused on promises as an API.
Deal with this race condition.
And to be honest with you, the API for promises is the least interesting part to me. It's far more interesting to me that promises are a codification of this pattern built in for us so that we don't even really have to think about it as much. It's even there for us automatically. A codification of this pattern of managing state internal inside of a wrapper in a time-independent way. There's more.
Because that's exactly what is doing this Thunks. Is the ability to maintain the states of a value in a time-independent way.
More to promises than that, but
the ability to maintain. Okay, Jesus. So Thunk is Thunk. The ability to maintain a state. The ability to maintain a state in a time-independent manner.
A codification of this pattern of managing state internal inside of a wrapper in a time-independent way.
Exactly. Thunk, the ability to maintain a state in a time-independent way. Thunk. The ability to maintain a state in a time-independent way. Okay. The ability to maintain a state in a time-independent way.
There's more to promises than that, but that in and of itself is revolutionary. That in and of itself is bringing to the masses something which we could have been doing all along, but for whatever reason, this wasn't something that we spent time thinking about. I've written an awful lot of really bad asynchronous code. I wish I could go back and fix all of that stuff to have been using a pattern like Thunk's, because this would have been a lot better than what I had before. But it's not the end of the story. There's more to go, much more to go in this workshop. So with that as our foundation, as a reminder of where we're at and why Thunk's are so important, let's dive in and talk about promises.
Okay, that'll be all for this video. Take care. Bye-bye.